Okay, welcome back. This next lecture is going to be on intermolecular forces and how they affect physical properties of molecules. The first thing you should do is go ahead and try and write 4 more constitutional isomers of hexane. And so you can pause the screen and try and come up with 4 of them. These will be molecules that have the same molecular formula but a different connectivity, and they're going to have different physical properties that we'll investigate. One of the easiest ways to draw additional constitutional isomers is if you start with a long chain. You'll know that if you make another 6-carbon chain, it will be the same exact molecule, hexane. And so to draw constitutional isomers, what we're going to have to do is put in branches or kinks in the chain. And so if we start with a 5-carbon chain, then as long as we don't put the 6th carbon on one of the ends, we'll end up with a different molecule because we have changed the carbon backbone or the connectivity. And so these are 2 examples that work. Now, for example, the next logical spot to put a new branch might be on the 4th carbon from the end. However, this particular molecule would be identical to the first one that I drew. All that's happened is it's just been flipped around, so the connectivity is the same. It's the same molecule. So this one doesn't count. It's simply repetitive. Now these aren't the only 2 we can draw. We can draw 2 more. We've extended our options for a 5-carbon chain, so now we'll start with a 4-carbon chain. The only 2 options with a 4-carbon chain are to put the branches on 2 of the inside carbons or both branches on the same inside carbon. These are the only structures that won't reproduce. What's interesting about these structures is that they all have different boiling points, and we'll analyze this data. What we can see with this data is that there's a large effect or significant effect that occurs upon branching with these different constitutional isomers. Notice the highest boiling point is with hexane, or the straight chain alkane. And this is because it has the highest surface area. Branches will reduce the surface area as the structure kind of gets balled up on itself. And so rather than being large and flat with lots of surface, it gets less surface area. Surface area is important because it ties into all of the potential interactions, specifically with these structures, van der Waals interactions. And so we mentioned van der Waals interactions in class. All molecules possess them, so the more surface area, the more van der Waals interactions. When you have more van der Waals interactions between molecules, then that allows them to stick together more. And so boiling a solution is providing enough energy to break all of the interactions between molecules that allows them to go into the gas phase essentially one at a time. So you can't boil a substance without breaking all of the interactions. And so we have the most surface area here. When you have one branch, the boiling points are different. They're different molecules. These will actually have different surface areas. And we can see that with one branch, we get a drop in boiling point. It's easier to boil the molecules. When you have two branches, another drop in boiling point. Especially when they're branched on the same carbon here, we're really balling up that structure so it's not spread out with lots of surface. So one thing we can say that will always be true is that branching decreases surface area, which will always decrease the interactions that are there in a given set of molecules. So we can work with another set of molecules where we'll change the functional group and see the effect on boiling point as well. These three molecules are all similar surface area, similar molecular weight. However, there's a difference in the type of functional groups that are there. When we go from a molecule that only has van der Waals interactions, we see a very low boiling point in this series. When we go to a molecule of similar surface area that has a very polar bond, so we get a permanent dipole-dipole interaction, we see a large increase in boiling point because these molecules can be strongly or moderately strongly interacted with each other such that it's hard. It requires a lot of energy to break them apart and take one into the gas phase. Here, not only do we have a dipole-dipole interaction because of the polar carbon-oxygen and hydrogen-oxygen bond, but also the capability for hydrogen bonding, which is a very strong interaction. So the alcohol groups can hydrogen bond with other alcohol molecules, and it's very hard, requires a lot of energy to break those apart. This same effect with molecular interactions can be observed with the melting point of a solid becoming liquid. In a solid, those molecules will be strongly interacting with each other because they're confined in a tight space. And so breaking those interactions, allowing them to flow freely in solution, will require energy. In this case, the trend is not so striking, especially when we go from dipole interactions to hydrogen bonding, but the overall trend is the same. We can see we're at very, very cold temperatures, and it's taking more and more energy to convert the solid to the liquid. So this series shows how boiling point or the melting point increases when we go from very weak van der Waals interactions only to a combination of van der Waals and dipole-dipole interactions to a molecule that's capable of van der Waals, dipole-dipole, and hydrogen bonding. Another example over here is now with the same functional group, but we've got a tertiary amine versus a primary amine. The tertiary amine does not have a nitrogen-hydrogen bond, so it's not capable of hydrogen bonding. The primary amine, however, does have those nitrogen-hydrogen bonds and is definitely capable of hydrogen bonding. And we'll see how this affects the boiling points. Case where we have hydrogen bonding, a much higher boiling point is observed for this compound. And here, the same molecular weight, same surface area, same functional group, but very different boiling points based on that capability to hydrogen bond, which is really important for predicting properties. We saw some evidence of the effect of molecular interactions with melting points, and that's a strong contributor to being able to predict a melting point for a given molecule. So we can say that melting points increase with the strength of molecular interactions and are affected by symmetry. Now this is kind of an odd effect. Essentially, a very highly symmetrical molecule will tend to have a high melting point because very highly symmetrical molecules will be able to pack together into a crystal structure very efficiently, and it's hard to break up that structure. And symmetry will only apply to melting points, not to boiling points. For example, we'll have two constitutional isomers and look at their melting points. These two structures are barely different. Here we've got a branched alkane, and here there's just two branches. And so it's a 3-carbon chain with 2 branches coming off that center carbon. Here is a 4-carbon chain with just 1 branch coming off one of the internal carbons. The effect on melting point is huge. This is a very, very low melting point, so it's very easy to melt this solid. The melting point on this structure, because it's so highly symmetrical, and the shape is actually tetrahedral, and we can build a model of this and examine it. But because of that symmetry, it packs very tightly into a crystal structure, and then it's hard to break that up into the liquid form. So it requires a lot more energy than a molecule that's very similar that does not have that high level of symmetry. We'll see more examples of this in class and in the book. The next thing we want to discuss is solubility. And factors that influence solubility are actually the same as those that affect boiling point. So these two things go hand in hand. For solubility, we basically have two types of solvents that we consider. There's aqueous, which just means water containing. So it could be a water organic mixture. Normally that means a water, primarily water-based solvent. And then organic solvents. Organic solvents are simply solvents composed of organic molecules, and there are hundreds of different kinds of organic solvents. I apologize for that typo. Mainly as organic chemists, we're interested in just knowing the aqueous solubility of molecules, because organic molecules tend to be soluble in most organic solvents to some degree. And so we're interested in their solubility in water for many reasons. For aqueous solubility, if you have polar bonds or polar functional groups, that tends to increase the aqueous solubility. Water is a polar molecule that can hydrogen bond, so it likes to take things into it in solution that are also polar, and especially if they can hydrogen bond. So the first two are what it likes, what water likes for solubility. The third one is basically what it rejects. Water does not like to allow into its solution hydrocarbons. Hydrocarbons have very low polarity, they cannot hydrogen bond, they disrupt hydrogen or water's hydrogen bond network. And so anytime you have a large hydrocarbon chain or group on a molecule, it will reduce its water solubility. Small hydrocarbon chains, like 1 or 2 carbon chains, will disrupt it a little bit, but usually if you have a good polar group on the molecule, that's enough to allow it to dissolve in water. So we have some data to examine that will wrap up this portion. These two molecules are completely water soluble, and so acetone cannot donate a hydrogen bond, but it has a very polar carbon-oxygen bond and very small hydrocarbon groups, and it's completely soluble in water in any proportion. Ethanol can hydrogen bond and it's a polar molecule, it's completely water soluble. We can compare these two molecules to acetone, and we can look at their solubilities as we increase the amount of hydrocarbon group on the structure. For this ketone, only 27.5 grams per 100 milliliters, which is a lot, will dissolve in water, but it's not an infinite amount that will dissolve, but a pretty large amount. When you add one more carbon onto that chain, it drops significantly to just 5 grams per every 100 milliliters of water. And so that's a drastic change in solubility. If we look at a 3-carbon alcohol, which is propanol here, it's also completely soluble. As we get to other molecules that have increased hydrocarbon chains, the solubility in water drastically reduces. So even though we have a hydrogen bonding end, this is not completely soluble. When we add another carbon on, that solubility is reduced even further. And so we'll consider more examples, and there's more problems in the test, or in the text. But this should give you an idea of how the functional groups and knowledge of the interactions between molecules allows you to predict their solubilities, their boiling points, and even their melting points. One thing to add about solubility is that it's not only the presence of a single group that can impact the solubility of a molecule, but the more groups that are polar, or perhaps the more groups that can hydrogen bond. The more of them you have, the more likely it is to be soluble in water or to have higher solubility in water.